Okay, welcome class to Physics 390, class 28. This class is on the EPR paradox and Bell's inequality. The EPR paradox is a thought experiment which is meant to show that quantum mechanics is incomplete, that it's not a full description of physical systems, and that if we take quantum mechanics as a full description, we get the possibility of faster than light communication between parts of the system, which seems to be violate special relativity. So the EPR paradox was supposed to be indicating that quantum mechanics was incomplete. Something needed to be added to it in order for it to conform to special relativity. However, Bell's inequality, which came along much later, about 30 years later, showed that any extension of quantum mechanics with a local hidden variable, which would represent aspects of quantum mechanics not included in that theory, any local hidden variable theory is incompatible with the results of quantum mechanics. So it basically showed that the hope of the EPR paradox creators was not going to be realized, and that quantum mechanics is fundamentally non-local, and so stranger than we normally think. So let's get into the specifics. This comes from chapters 12.1 and 12.2 of our textbook. So first, a little bit on the philosophy of quantum mechanics before we get into the EPR paradox. So broadly speaking, there have been three philosophical positions that physicists have held with respect to quantum mechanics. The first one being a realist position, saying quantum mechanics is basically sound, it gives accurate results, but it's incomplete. There are further variables needed for a full description. So quantum mechanics, it's not that it's anything it has in it is incorrect, it just needs to be supplemented, and information is missing in some experiments and some theoretical treatments needed for us to fully understand. And that's the realist position. The orthodox position, which is the most probably the most widespread, is that quantum mechanics is in fact complete, and that the random element, for example, in the collapsing wave function, which is what really bothers the realist philosophical holders of the philosophical realist position, is unavoidable. So that there's a randomness, and as we'll see, a non-locality built into quantum mechanics, and so built into nature. The third position is agnostic, and that's to say all this arguing about philosophy is not really productive. Quantum mechanics just works. It's a super accurate theory. All of our technology, or most of our technology, is based on it, and just not to worry about these subtleties of interpretation. And there were a reasonable number of people who just decided not to think about these philosophy and foundations of quantum mechanics. Okay, so these three positions here. So which do we hold now? So let's find out. So in the Einstein-Podolsky-Rosen, or EPR paradox, which was proposed in 1935, just about 10 years after the main quantum mechanical theories were put forward, we have, one version of it. There are several versions of it, but the version we'll look at here and in the textbook is that we take a neutral pion and it decays into an electron-positron pair, which fly off in different directions. So here's our neutral pion, pi is 0 for neutral, and it decays into a positron zooming off to the right and an electron zooming off to the left. We'll assume the positron is at rest, so these move off just with equal velocities and equal speeds in both directions. Now, it turns out the pion has spin 0, so it's a boson. So because of that and conservation of angular momentum, the electron and positron must be in a joint singlet, because singlet is a spin zero state. Okay, so when we combine two spin a half particles, the electron and the positron, when we combine them in this way here, this is the spin singlet state, and the total spin is zero. So that's the same as the pion spin, and so we conserve angular momentum. Now, one thing to notice here is that the possibilities here are that contained within the singlet state is that the electron can be spin up, but if it's spin up, then the positron must be spin down. And conversely, if the electron is spin down, then the positron must be spin up. There's no component of this singlet state where the electron is spin up and the positron is spin up, or the electron is spin down and the positron is spin down. Those are simply not part of the singlet state. Okay, so we find experimentally, if we do an experiment like this, that the spins of the electron and the positron are in fact perfectly anti-correlated, regardless of the distance between the particles. So we can let this decay happen and let the particles go a few millimeters, 10 meters, a kilometer, and we still find that if the electron is spin up, the positron is spin down. If the electron is measured to be spin down, then immediately it forces the positron to be spin up to conserve this angular momentum and have, according to this singlet state here. So it seems as if if we measure the electron and that we get spin up, then the information that the electron is spin up is traveling instantaneously over to the positron, which then is forced to be spin down. And that was the crux of the EPR paradox. They said it shouldn't be possible for the information about a spin measurement result, for example, from the electron, to travel faster than light to the location of the positron and force the positron to be in a particular position. Because this faster than light travel violates the principle of locality. And according to special relativity, faster than light travel can lead to violations of causality, which gets us into real logical trouble. So that was the EPR paradox, trying to show that there was something incomplete here. So the proposal of the EPR paradox to resolve it is that the particles, the electron and the positron, must have had their spin states set immediately after being created at the pion decay. So even though it's not shown in the wave function here, both possibilities are present. Somehow not contained in the quantum mechanical description, which is this spin wave function of the two particles, it must have been embedded somehow in a fuller description of the system that the electron was in fact spin up and the positron was spin down, or in other cases, the reverse. But this is set immediately after creation and not after the measurement. So these true spin states would be called hidden variables because they're not part of the quantum mechanical description. Okay, so these would be local hidden variables. So after the EPR paradox, a number of physicists and theoreticians tried to come up with local hidden variables theories that described accurately the results of these decays and supplemented quantum mechanics in a way that avoided this faster than light travel of the information and apparent violations of causality. Okay, so what happened? Well, what happened was in 1964, a guy named John Bell, an American physicist, proved that any local hidden variable theory of the kind that we're talking about, with extra variables to supplement quantum mechanics, is in fact incompatible with quantum mechanical results. So if we try to add extra variables that contain more information to quantum mechanics, it invalidates, or it disagrees with the more limited quantum mechanical results. All right, so let's see how that Bell an outline of how Bell established that. So imagine the same pion decay. Okay, so here's the pion, here's the electron, here's the positron coming off, but with independent detector orientations A and B. So here's A, here's B. Now they're not in the same direction. So it's not two spin up detectors. This would be like spin at some angle here and spin at some angle here. Okay, so independent detector orientations A and B, which are vectors in space. So what Bell did is he calculated the average value of the product of the two spin measurements at A and B. So you would take, for example, to do a pion decay, take the spin measurement at A, he'd either get +1 or -1. The spin measurement at B, he'd get plus or minus 1. Multiply those together and either get 1 or -1. And record that in a table, do another pion decay, get + or -1, total all those up and take the average. And that would be called PAB, where A and B are the orientations here. And this average would depend on the orientations A and B. Okay, so, all right. So certainly a reasonable thing to do. It's not clear what it's going to yet, where it's going to get us, but let's follow along. So it turns out the quantum mechanical prediction, not predication, but prediction, is P of AB is equal to minus the dot product of A and B. Okay, so you can show this using quantum mechanics and do some work with the spin states. And so, for example, just to show that this is plausible, if B equals A, so these vectors here line up in space, so those are parallel detectors, then if we put in A for B, we get minus A dot A or -1. So the average value of the product would be -1, which represents perfect anticorrelation, because the only way you can get -1 is if one is +1 and one is -1, or the first one is -1 and the second one is +1. So that represents perfect anticorrelation. So at least this formula is plausible in that it's compatible with the anticorrelation was associated with the first EPR paradox argument that we looked at before, where the two detectors were parallel. Okay, continuing on, assuming that there was a hidden variable, call it lambda, which is containing the actual spin states right after the two particles, the electron and the positron, were created. Bell defined a function A of the orientation of the first detector, lambda, for the electron measurement, and B of the B orientation, lambda, for the positron measurement. For a given value of lambda, that would tell us what the electron measurement would be. So depending on the hidden variable, this function would tell us what the measurement of the electron measurement would be. And similarly, the function B would tell us what the positron measurement would be at the location of the detector with vector B as its orientation. And each of these takes on only the values + or -1. Okay, it's either got to be up or down in the direction of the A or B vector. Okay, so we've got these A and capital B giving us the values according to the hidden variable lambda for the actual measurement of the spin state at both positions. Okay, so then how would we write, in terms of these new A and Bs, how would we write our average value of the product of the two spin measurements? Well, we'd have P of A and B would be the integral over the distribution P of lambda of the hidden variable of the product of the A and B for that particular value of lambda times d lambda, where again, P of lambda is the probability density of the hidden variable. Now that probability density, like all probability densities, must be real. It should be positive because there's no chance of a negative probability. And it has to integrate to 1 since the lambda variable should have some value. Okay. So this would be the, depending on the distribution of the hidden variable lambda, we would get different PABs. And also depending on the functions here, how lambda affected the measurement of the positron at B and the electron at A. Okay, so this is how the average value of the product of the two spin measurements, PAB, could be written as a function of the hidden variable, which is determining the two states as they come out. And then these functions, which take that hidden variable and determine the actual results of the spins at those two locations. Okay, so we're going to use this formula here in a second, and we're going to get to the crux of Bell's inequality and the crux of his argument here. So Bell's inequality and non-locality. So we can find with a short argument and see the text for this. It's about 3 or 4 lines. Using this definition of PAB, that is the integral of P lambda and so forth. And we introduce a third detector orientation. So we have A, B, and C. And we find from this definition and a few algebraic manipulations that the following inequality must hold for any local hidden variable theory. Okay, so any particular hidden variable lambda and any distribution of that lambda that we have. Not many restrictions, not really any restrictions at all on the type of local hidden variable theory. We find Bell's inequality, which is that the absolute value of PAB minus PAC should be less than or equal to 1 plus PBC. Okay, well, that's all right. That looks nice, but what does it get us? Okay, let's see how this argument, remember, this inequality holds for any local hidden variable theory, no matter what hidden variable you propose to determine the spin states of the electron and the positron after they emerge from the pion, and any functions capital A and capital B for how those hidden variables affect the spin measurements here. So any hidden variable theory as expressed in the lambda variable and these A and B functions. This inequality must hold for all of those possible theories. So it's extremely general. Okay, so if we choose the 3 detector orientations, our A, B, and C as shown below, so we have A in the X direction, B in the Y direction, and C at 45-degree angle. And we use the quantum mechanical result that P of A and B is minus the dot product of A dot B, then the quantum mechanical result would be P of A and B here would be 0 because the dot product of X and Y is 0. Meanwhile, the dot product of A and C would be the cosine of 45 degrees, which is root 2 over 2 or 0.707. Then there's this negative sign. So it turns out to be minus 0.707. Similarly, the dot product of B and C or PBC would be minus the dot product of B dot C, but that's minus square root of 2 over 2 again, since it's a 45-degree angle. So it's also minus 0.707. Okay, so this is the quantum mechanical result for this particular choice of 3 detector orientations that we have here. So inserting these values into Bell's inequality, remember Bell's inequality should be satisfied for any local hidden variable theory to work. We get PAB minus PAC, which would be 0 minus 0.707 or 0.707 on the left side. On the right side, we have less than or equal to 1 and then plus PBC is minus 0.707. So 1 minus 0.707, which is 0.293. So we get Bell's inequality says 0.707 is less than or equal to 0.293, which is not true. Okay, so Bell's inequality is violated here. So quantum mechanics for this three orientations here, and this result, which is solid in quantum mechanics, violates Bell's inequality. Okay, so this shows that quantum mechanics is not compatible with any local hidden variable theory, because this Bell's inequality, remember, held for any local hidden variable theory for any lambda function A, function B, very generally. So no matter what you came up with for your hidden variable theory, this inequality should be satisfied for your theory, but quantum mechanics itself doesn't satisfy it. So it's not compatible with your hidden variable theory. Okay? So that's kind of a big deal and a very general and powerful result. And definitely Bell's inequality, and which is part of Bell's theorem, is one of the most, what would you say, sort of deep or profound theoretical results of the last 100 years. That's what many physicists think anyway. Okay, so what does this mean? Well, first of all, Bell's inequality here has been tested experimentally in a number of systems, not just pion decay with electrons and positrons, but decay of particles into photon pairs, gamma ray pairs, where we have polarizations as our measurement instead of spin, in systems of atomic transitions. So a variety of systems that quantum mechanics applies to, and most famously by Alan S. Bay et al. In the 1970s, was kind of the touchstone experiment for this. And it turns out that Bell's inequality is always violated. So the hidden variables theories can't work to describe the experimental results. So the conclusion seems to be that the local hidden variables theories don't work. So nature is somehow fundamentally non-local. We can't come up with a local hidden variables theory to supplement quantum mechanics. So nature is fundamentally non-local. This is strange. We like to think of things as local. So it's really weird to think that this, when the electron is measured to be in a certain state here, that right away it forces the positron to be in a certain other state here. But that seems to be the way nature works. Luckily, or for our kind of logical coherence of our physics, the non-local correlations, say between spin states at large separations, can be shown not to be able to send information faster than light. So even though there's a correlation between these two spin states when one is measured and the other is forced here, it turns out there's no way to use that for someone to sit here and send a signal to someone sitting here in a way that meaningfully communicates information. So since there's no send information faster than light, there's no violation of causality. So note, although Bell's inequality seems to have or has eliminated the possibility of local hidden variable theories, there's still the possibility of non-local hidden variable theories to supplement quantum mechanics. So to try to increase our knowledge of the system beyond what quantum mechanics provides, where there are hidden variables which are non-local, because nature is fundamentally non-local. So that's possible, and is certainly something that is researched by some physicists now. Okay, so just a brief summary. We've looked at the different philosophical positions: the realist position, the orthodox position, and the agnostic position. It seems now that the orthodox position is the one to hold, that in fact, quantum mechanics, this uh, collapse of the wave function and the propagation of that information of the collapse of the wave function faster than light, even though it doesn't violate causality, seems to be part of natural description of things. The EPR paradox was a very creative way to test quantum mechanics and to be provocative in trying to put its ideas to the test. Suggested that there should be local hidden variables theories which could supplement quantum mechanics and get rid of this kind of action at a distance, this propagation of the information across faster than light. But Bell's inequality and Bell's argument showed that any local hidden variables theory is incompatible with the results of quantum mechanics itself. So it can't be used to supplement quantum mechanics. And it's been tested experimentally and is considered to be very solidly established now. So we have nature as fundamentally non-local, but causal, and still things to be discovered, perhaps non-local hidden variables theories to augment our understanding of quantum mechanics. Okay, thank you so much for your attention, and I will see you all in class.